Any questions?
Would you do the kinetic energy problem where?
Somebody has not taken it yet.
Oh, okay,
So-
sorry.
Any questions other than the quiz you just done?
Okay.
That about the quiz. Ah. Good. I'm gonna do something that I think it's everyone's favorite thing, a derivation. Now, again, the reason I'm going through it is just to show that the stuff comes from somewhere as opposed to just sort of going, there it is. But the first question is, if I've got something pivoting about a central axis, or an axis. So for example, this could be an overhead view of a door. And this thing is swinging around. And this is swinging around. That's really not much better. What I want to know is, what's the kinetic energy of the door? So, you all know the formula. Here we go. What's the formula for kinetic energy?
1/2 times m times v squared.
Not quite the unison I was hoping for. Matter of fact, it was a little bit quieter than I was hoping for. But all right, so we have kinetic energy 1/2 mv squared. Mass of the door, yeah. You can stick it on a big enough balance, you can figure that out. But what speed do we use for the door? So what I'm getting towards is, as this thing is spinning around, let's say it's going to go all the way around in a circle. If I take a spot here, and we'll just say that's 0.1 meters from the hinge, and a spot here, 1 meter from the hinge, which is going to take more time to get all the way around? That's going to take more time? Yeah. Anyone with a different answer?
I say the lower one.
Say it again?
I said the lower number.
Okay. Anyone with a different answer? There are only 4 possible choices. It's that one, it's a tie, or neither, because the door won't do that. I'm assuming that the door can do that, so let's throw out that last choice. Anyone for a tie? All right, so let's just do a simulation here. Make sure I'm not going to hit anything. All right. So I got my arm like this, and just do a crude estimate of time. So imagine I got a point here, and I got my wrist and my shoulder. And think about the amount of time it takes to go all the way around in a circle. How much time did it take, roughly?
The same.
I hope it's the same. If it didn't take the same amount of time, then something's wrong with my arm. Just like with the door, if it takes a different amount of time for those 2 spots to go around in the circle, then that door is not much of a door. So one thing that we're dealing with here is a rigid body. We are assuming rigid body. So that every point on there, if it's rotating, every point on there will take the same amount of time. Now the question is, which spot is traveling faster?
The smaller number. Because it's closer to the axis.
Okay. Anyone want to disagree or
I
agree?
think the farther one, since it's traveling a further distance, it has to go faster.
That's which one was faster, right?
Which one has a better or higher speed?
Oh,
Higher speed?
yes,
Yeah, okay,
speed.
yeah. So you're going, so we got, again, the two choices, it's that one, or a tie.
I think it's a tie. Now,
So you, well, let's have an opinion. Everyone in here, have an opinion. We're gonna see if physics by democracy works. So I'm gonna call this point A and this point B. So A, B, or tie. The question is, which will be traveling faster, higher speed? A, B, or they have the same speed? All right, who says A will have a higher speed? Who says B will have a higher speed? 1, 2, 3. Who says a tie? 1, 2, 3, 4, 5, 6, 7, 8. All right, so which one's faster, the higher speed? What is speed anyway? How do you find it?
Distance times time.
Almost. It's not distance times time.
Divide by that.
Yeah. All right, so it's the distance traveled over the time it took. So I've got this point B, which is traveling around that circle. And I have point A, which is traveling around that circle. What is the distance that A travels? Or formula? Or conceptual shape? Something
radius.
I heard a voice.
Is it the radius square?
Oh, the pi r squared is the area.
Okay.
What are we looking for here? Not the area.
The distance of travel,
Okay,
beginning to.
so it's traveling in a circle, so what is that distance called?
Circumference.
That's the one. And the formula for circumference? There are generally two formulas that people remember for circles. It's not pi r squared, it's the other one. Well, I figured at least somebody would remember the formula for the other formula.
I don't know why I'm blanking.
2 pi r.
That's the one. All right, so this is gonna travel, well, the radius is 1 meter. I know that the distance around here is going to be 2 pi r, so that's, since the radius is 1 meter, that's 6.2. I said it correctly, read it wrong. It's roughly 6.28 meters. This one, shorter radius, shorter distance, this is going to be 0.628 meters, approximately. So the one that travels the bigger distance, well, that'll be A, the one that's farther away. So congratulations to those two people. So if A travels a larger distance than B, but it takes the same amount of time, which one's traveling faster?
A.
Yes. If we can stick with simple numbers here, let's say it takes 10 seconds to go around. So if that's time, then the speed of A is going to be 6.28 meters divided by 10 seconds, or 0.628 meters per second. And the speed of B, that's not much better, is 0.628 meters over 10 seconds, which is 0.0628 meters per second. So A is going to be traveling faster. It travels a larger distance, but it takes the same amount of time. How many of you have seen the movie Ben-Hur? Okay. There's a chariot race in there, a famous chariot race. And one of the suggestions for the chariot race is you put the faster horses on the outside, because the horses on the inside, since you're traveling in a loop, an arc, the horses on the inside aren't traveling as far, so you want the faster horses on the outside for situations like that. Or if we held hands, one person in the middle, and we all stretched out, held hands, and we started moving around, but the person in the middle just moved around at this pace, the person on the outside has to run to keep up, to keep that line straight. Just because they have much farther distance to travel. So let's take the next step. For things, we were talking about things that are rotating. It's traveling in a circle, so the distance traveled is going to be 2 pi r, and the time is just going to be, we'll just assume going around once is the period. It's the period. And what is the period?
One. You said it's
In general,
oh,
what is the definition of period? Math-wise.
from where it started to where it goes back to where it started.
First off, what? Yes, almost.
Almost, I know. It says.
Why am I using a T for period?
Time?
Yes. It's the time it takes for an object to get back to where it started. So basically, if I have anything that has repetitive motion, period is how long it takes to do it once. So, time to do one cycle of repetitive motion. So the period of Earth's orbit is 1 year. It takes 1 year for the Earth to get to go all the way around the sun. And it takes roughly 28 days for the moon to circle the Earth. So that is the period of the moon. 27 point something. So I have this 2 pi r over t. And I'm just going to pull r off to the side here. So I have 2 pi over t times r. So when we're talking about a circle here, we're talking about going around once. What is 2 pi in a circle? Partly checking math backgrounds here.
6 point.
But this is roughly 6.28. But what does a 2 pi have to do with a circle?
It's the radius?
Say it again?
It's the radius?
Yeah, it's the number of radians in a circle. What's a radian?
A degree circle?
What did you say?
The half,
The half?
like half was circle like that, and then like that. The other half so it would be 2.
Oh, okay, yeah, half the circle would be pi radians. But what is a radian? Have I done the Babylonian bit? Nope, all right. Why are there 360 degrees in a circle? Blame the Babylonians. All right, so here's a quick and dirty history of angles. The Babylonians felt that 60 was an important number. Matter of fact, they had a base 60 system. Seems odd, but it seemed to work for them. And the nice thing about 60, the reason why it is there are certain numbers that have just a lot of things that go into it. Body temperature was originally 96. That's what Fahrenheit figured out, because there were a lot of numbers that go into 96. Made the math easier. But the numbers that go into 60 evenly, 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. All those numbers go into 60. So 60 had this special meaning. The other thing that had special meaning, the Babylonians were sort of that, and the Greeks sort of latched onto this, or I'm not quite sure how the cross-pollination happened, but there was something special about an equilateral triangle. Just all the sides are the same length, all the angles are the same. So if you combine those two, you say, well, this is a special figure, that's a special number, let's combine it, and let's just make that 60, 60, and 60. And now I've got this thing of 60, so if I take 6 of those wedges, hopefully drawn better in your notes. That is horrible. Not that one. They will form a nice section there. They'll blend nicely. Think Trivial Pursuit, the wedges in Trivial Pursuit. And now I have 6 of these things, so 6 times 60 is 360. That's where we get 360 from. It is clearly man-made. And the mathematicians really want to get rid of as much man-made stuff as possible. They want to see what the purest form of it is. And so, especially in the 18th, 19th century, especially in the 19th century, there's a big effort to get rid of all mathematics that was based upon what people decided, and see if there was some natural structure to all of it. And so, what they noticed, you take any circle, all circles have a radius, that seems natural. If I take that radius and I wrap that, so imagine I've got a circle here, I have a string that's the length of the radius, and now I'm just going to move that string along the edge here, and then go back to the center. What they noticed is that this angle right here was the same for every circle. That, they figured, was not man-made, and so they said this is something that just comes with nature, and so that is what they called 1 radian.
So the length of the radius is the same length as the angle? Would you?
The length of if I take any circle, I take the radius, and then I wrap the radius around the edge. That, and then I draw basically a line back to the center. That angle is the same for every circle.
That angle's the same.
And that's what's a radian. And since this length, arc length here is a radius, and I know around the circle is 2 pi radii, then there must be 2 pi radians around the middle. So radian is just a different unit. There's 2 pi radians, same as 360 degrees, and the same as 400 radians, which I don't think show up on calculators anymore, but they used to. Never seen anyone actually use this, but it was on the calculator when I was, I guess, your age. So, I've got 2 pi radians here. This is actually 2 pi radians divided by time. So that is an angle over time. So flash back to what we did last week. What is the change in an angle over time? This is when we had it. We had the set of scalars, and we had the translational linear vectors, and then we had the translational analogs. Sorry, the rotational analogs. They're just speaking all day long.
The position?
Not
No,
position.
am I looking at?
Let's do what's the rotational, or what's the linear analog of angle?
Data?
Theta is the angle, what's the linear analog?
Am I looking at the wrong chart?
What'd you say?
Velocity.
That doesn't answer that immediate question, but you're partially answering another question I asked.
Because we did linear and transitional motion and rotational.
Yeah.
So that's what I was looking at.
All right, there's your angle theta, and then
Oh, so you're asking for
position.
S or X?
Because we had all the formulas, we had all the linear formulas, and then we just transliterated into the angular formulas. And so now I'm asking, this is my angular formula. And I'm asking what the linear formula is. And so the equivalent of angle, or the analog of angle, is position. Not worrying about vector symbols right now. What about time? What's the linear equivalent of time, or analog?
The same?
Yep, it's time. What is distance over time?
Displacement? Displacement?
The distance over time. Yes. So what is the angular equivalent of speed? I don't think I had speed written down there, but what's the angular equivalent of velocity,
Omega,
which stands for?
angular velocity.
So what is the angular analog of speed? Make the leap. The angular analog of velocity is angular velocity.
Is it the same thing?
The angular analog of speed is,
Angular speed.
that's it, which is just omega without a vector symbol. So what I'm getting towards here is that if I have something going around an entire